Hey guys, welcome to our lesson video for this week. This one is going to be more kind of like what we were doing back on Google Classroom. I decided just kind of make your lives a little bit easier. We're going to do more of this, kind of just taking the notes, doing what you can. Hopefully, you are learning what you're learning about it. I'll have more of a bigger update video tomorrow going over all of that. But for now, this is just the lesson. Homework is very simple. Take the notes, copy them down, and you get all the notes down, and you get full credit, kind of like we were doing before. Should be nice and easy. I'm sticking along with what that student suggested, where I write down the notes first in advance and just read them off, kind of slowly, talk about them some more, and then do the actual examples in the middle of the notes. Please note that today I'm going to say that we're going to be erring more on the side of memorization than total full understanding. I'm going to admit that. But we will get closer and closer to that understanding sooner rather than later. And yeah, we're just going to go through it. All right, so lesson title is End Behavior for Rational Functions. So end behavior for rational functions. That's Rational. Sorry for the terrible spelling, handwriting. The essential question here is, how do I find the end behavior for rational functions? And the objective, which you do not have to write down that objective at the top, just a reminder, but it's just kind of telling you what we're going to be doing, is I can find the end behavior of rational functions by comparing. This is what you're going to do. You're going to compare the leading term, this is term, T-E-R-M, that's just a single R, of the top and bottom. The top being the numerator, the bottom being the denominator. So you don't have to start writing the key idea part yet. I'm going to be talking about that later. I do have a vocab word here on the previous page. So if you haven't finished copying at least that stuff in blue up at the top there, go ahead and pause. If you missed a word that I said, you can rewind, hear what I said one more time. But I'm going to turn this page over in a second, so pause if you need it. Turning the page over. You have one word to write down. You don't have to write down the separate page. I just like doing it. The word to write down is the rational function. So a rational function is any function which can be written in the form of polynomial divided by polynomial. So we have that previous definition of a polynomial. It's what we've been working with in all the previous last 5 or 6 lessons. You have the x squared to the 5th, or 7x squared to the 7th, whatever it was, all that stuff, x to the power. This time we're going to do the same thing, except now we're going to have 2 of them, one in the top, one in the bottom, a fraction of 2 polynomials. So if you wanted to write that as your own definition, a fraction of 2 polynomials, you can. But this is the easy definition. Any function can be written in the form of polynomial divided by polynomial. All right, I'll turn it back over now. Again, pause if you haven't finished it. We're going to start with a key idea. So for the key idea, there are 3 cases. We're going to go through the 3 cases on 3 separate pages. And for all 3 of these cases, we're going to say let n be the degree of the numerator. So that's, again, that word from a previous lesson, that polynomial degree. And let d be the degree of the denominator. So case number 1, the numerator degree is greater than denominator degree. So it says, if the degree of the top is greater than the bottom, reduce the fraction and refer to old lessons. Whoof. Let's watch it happen on example 1 here. So example 1 is, again, a case where the numerator is greater than the denominator. Let's see it happen. You need to find the leading term of the top and bottom first. That's definitely step 1. So you're going to have a leading term at the top, and you're going to have a leading term in the bottom. Just like the last time, you're finding the lead term in exactly the same way. So the lead term in this case is going to be -2 times 5x all squared multiplied by x.
Hey, welcome everybody.
And I gotta pause my video just a second. Sorry, my other video thing freaked out on me and wasn't happy, and it just did it again. Okay, I gotta pause. Okay guys, we are back from fixing everything. So I've totally lost my train of thought. I was finding a leading term, it looks like. So I'm finding the leading term of my numerator here, the top function. So that leading term is going to end up being, holy moly, did I run out of room here? If you multiply this all out, that's going to be a 25x squared, so you get -50x cubed on the top there. And on the bottom, you get just x squared. So in the case directions, what I wrote was, if the degree of the top is greater than the bottom, reduce the fraction. What am I talking about? You're going to do the leading term dividing by the leading term. So you're doing negative 50 x cubed divided by x squared. This requires us to go back to even earlier lessons and deal with these exponents, but it's not that big a deal. Remember, when you're dividing the like terms, you subtract the exponents, so you have 3 minus 2, and you end up getting negative 50 x to the power of 1. And what happens on the negative 50 x to the power of 1? Well, that's x to the odd, negative odd, so it kind of looks like this. So that's it. That's the whole problem. End behavior. As x approaches infinity, we'll do as x approaches infinity, f of x approaches, in this case, negative infinity. Oops, this is supposed to be negative infinity. And f of x approaches, when it goes to the left, it goes up, so we got positive infinity. That's it. So honestly, these questions is not that big a deal. Finding it, we just have to first figure out the leading term, the top and the bottom, reduce the fraction. The reduced fraction is what you do for your end of behavior, and you treat it just like those previous problems. So a lot of the stuff is the same. But like I said, we have 3 cases, and the next 2 cases are totally different. So if you are not done writing this stuff down, I recommend pausing the video, writing the rest down. All right, no more chance to pausing. I'm continuing on. Case number 2. If the degree of the numerator equals the degree of the denominator, the end behavior is y equals a over b, where a and b are the lead coefficients. So like I said before, we're going to do a little bit of memorization, but this time I'm actually going to have a little bit better explanation as to why, using the previous example. We'll see in a second. We still have to do what we did in the last problem. We have to figure out the leading term for both. The leading term for the top is very easy. It's simply the largest exponent right away. It's negative 3x to the 4th. Done. Leading term of the bottom, we have to do a little bit more work, but it ends up being 2x multiplied by x cubed, which is 2x to the 4th. So the answer is actually really, really fast. The end behavior is y equals a over b. What I mean by a over b is, well, let's go ahead and circle a and b. Those 2 guys right there. It is quite literally, the answer is going to be y equals negative 3 over 2. Let's talk about y really quick. If we use the same technique as we did in the previous problem, and we just did negative 3x to the 4th divided by 2x to the 4th, well, the x to the 4ths cancel out completely. And if they cancel out completely, you just get this y equals negative 3 over 2. After that, we just have to write that end behavior out. As x approaches infinity, as x approaches negative infinity, g of x approaches, g of x approaches. And we're actually just going to write negative 3 over 2 for both of these. So it's our very first time that our end behavior is not infinity. That is to say, at the ends of the graph, it is going to negative 3 over 2. Before we actually finish this up, let's actually see that this is what happens on this graph. We're going to switch over to some Wolfram Alpha action here. If my open broadcasting software will let me switch. Okay, there I am. Goodbye, my face, and hello, graph. So we're going to go ahead and graph this guy. So we're graphing g of x. I'm literally typing it in as it appears. In order to do that, you're going to want parentheses around the top and bottom. So we have 5x to the 3rd minus 3x to the 4th plus 5, and then divided by, see, when you do the parentheses like that and do the divided, it immediately brings that up. We got 2x minus 1, and then times x plus 2 to the 3rd. All right, so I'm also going to go ahead and graph, like I said, that y equals negative 3 divided by 2. And if we zoom out enough, we can see that at the edges of the graph, that graph is approaching negative 3 over 2 on both sides at the ends of the graph. And not trying to scare anybody, but our goal is to be able to sketch this guy. That's gonna be our ending. situation. We're doing it piece by piece though. We're doing the end behavior here first. All right. I just want to show you that graph, give you that Desmos, because Desmos again will do that work for you, nice and neat. Let's get rid of this guy. Let's transition back over to my beautiful face. Okay. Anyways, point is, we actually have a very easy question when you have the numerator equals denominator every single time. It is a over b, which is just leading term, the coefficients in front. That's it, every single time. Top over bottom, goes infinity, goes the same number. Case number 3 is actually the easiest of all the cases. If the degree of the denominator is greater than the degree of the numerator, the end behavior is y equals 0. So let's do it. So the leading term here, if you end up multiplying that out, you end up getting 12x squared for that leading term. And this leading term here is going to be x cubed. And because that degree is greater than that, you immediately just write y equals 0. Why does that happen? Well, basically what's going on is the denominator is getting bigger faster than the numerator. Like if I were to plug in 1,000,000 here, the top would be 1,000,000 squared, but the bottom would be 1,000,000 cubed. So you're dividing by a larger and larger number. When you divide by a larger number, you're going to end up being close to 0. We can actually write this out. As x approaches infinity, as x approaches negative infinity, h of x approaches 0, h of x approaches 0. And again, if you'd like to see that this is what happens, you can go graph it on Desmos. I'm not going to do it for you right now. Hopefully we'll have a more full understanding of this later, but for now, you just need to know these 3 cases. Your first assignment next week is going to be a very short homework assignment of seeing if you actually understood all the stuff that we just did. If you'd like to, you can actually practice it right now and be a little bit ahead of the game for next week so you have less stuff to worry about. I know you guys have a lot on your plate right now. So right here, here's our homework for the first part of the homework for week 3 is describe the end behavior for the following functions. There you go. You got 4 problems there for you. Follow those 3 cases, and that's the only possibilities that you can even have. I went through those 3 examples. Hopefully you can repeat that situation, figure out which case you're in. If you don't want to do this homework right now, you do not have to, because all you got to do is show me that you finished the notes. That's it, guys. Have a wonderful rest of your day, weekend, week, whatever it is even anyways. Have a good one.